Welcome to Chandra's Edu. On August 17th, our channel has reached the milestone of 1000 subscribers. Thank you, all subscribers. Uh, this would not be possible without all your support. I am also expecting similar support in the future. And on this occasion, I am starting a new playlist on artificial intelligence course. And in this, firstly, we'll be discussing about the depth first search. So first we'll try to see what is search and why it is important in artificial intelligence, and later we'll try to discuss different search techniques, and then we'll move on to the present topic, that is depth first search. So in artificial intelligence we are trying to find solutions for the problems, and whenever we say a problem, so we need to follow some steps to reach to the solution, and that moving from the problem to the solution, that path we can call it as the search for the solution. So there can be different search strategies to reach to the solution from the initial state or the problem. So we have uninformed search strategies and informed search strategies. So in uninformed search strategies, the important strategies are depth first search. Next, we have breadth first search, as well as the uniform cost search, and even some more uninformed search strategies are there. We'll see as we proceed in the course. And what is an uninformed search and what is an informed search? Okay. So uninformed search, we have different names for them. So one name is blind search, and other name is nothing but exhaustive search. So that is for the uninformed search. And when it comes to the uniform informed search, so we can call it as a heuristic search. So we'll see first the differences between uninformed search and the informed search. So in an uninformed search, no information about the number of steps or path cast from the current state to the goal state is available. That means there is no information how many states we need to move to reach to the goal state, or how much is the cost of that path. So that is not known in the uninformed search. When it comes to the informed search, so path cost from the current state to the goal state is calculated, and here the intention is we know the cost, but we should select a path with the minimum cost. So that is the informed search, as we know the goal state and how much cost it will take to reach to that goal state is also known, so that it is an informed search. So uninformed search is less effective in search method. Why? Because we need to search all the paths to get to the final state or the goal state. As informed search, so we know already the paths to the goal state and even the cost of the paths of the goal state to reach to the goal state. So it will be more effective in the search than the uninformed search. So it is uninformed search is less effective, and informed search is more effective. And next, problem is solved in the problem to be solved with the given information. So we don't have any extra information for solving the problem or to reach to the goal state in the uninformed search. But in case of the informed search, additional information can be added as assumption to solve the problem. So as it's an informed one, we can take the additional information to reach to the solution. And coming to the different uninformed search techniques, we have breadth first search, uniform cost search, next depth first search, depth limited search, iterative interactive. So this is iterative deepening, iterative deepening search. Next we have bidirectional search. So these are the different uninformed search techniques. And when it comes to the informed search techniques, we have best first search, greedy search, and A star search. So these are the different search techniques. So we'll be going in a sequence. So first we have the breadth first search, but we'll discuss about the depth first search, and then we'll in the next video we'll discuss about the breadth first search. So this is what the depth first search is. So here we need to move deep to find the solution. So we need to dig deep to find the solution. So if the solution is not there in that path, we need to once again go to the top and search and dig somewhere to find the solution. So that is what the depth first search is. So here we are considering one example as a binary tree. So binary tree means, so bi means 2. So there will be a node. For each node, so there will be two paths. So wherever you can consider, here we have A. So we have B, C. When you take B, D, E is there. When you take D, H, I is there. You can take any node point. So there will be two paths, so that it is a binary tree. So in this binary tree, we are performing the depth first search. Okay. And so just see, this is, we are at the first node, that is A. So as we have two paths, so one path is nothing but to B and other path is C. So in the depth of a search, we'll always try to explore the leftmost path. Then we'll try to go to the next path if the solution is not there. So here as the leftmost is nothing but B. So it will move to B first, and in that B it will dig deep, that is to the leftmost of the B, that is nothing but D, and after going to D then it will dig to the leftmost of the D, that is nothing but H. So if the solution is not H, then it need to once again go back to D, and then it need to check I. So if I is not the solution, so what it need to do is it need to go back to D once again, as there is no solution, that is H and I are not the solutions. So it need to once again go back to B and then explore the other path which is left over, that is E. And in the E, so it need to check for the leftmost one, that is nothing but J, leftmost path J. Next, after exploring J, if the solution is not there, then it will once again go back to E and just check the other path which is possible for E, that is nothing but K. Even if K is also not the solution, then it will go back to E, as we have already covered the other path of the E. So it will once again go back to B, and even we have also covered the path, that is the other path D of this one, and also E. So there is no other path left over in this, so it will once again go back to A, and then it will go to C now. Why? Because all the left paths have been covered and there is no solution in that, so that it will now come to the node C. So it will check for the leftmost of the C, that is F. So it will come to the F, and from that F it will try to see the leftmost, that is L, and if the solution is not L, then it will return back to F and then check for M. And if M is also not the solution, it need to go back to F, and as the two paths L and M of the F are covered, it need to once again track back to the C, and then it will check the other path which is possible for C, that is nothing but G. So this will be continuing. It will just try to see all the leftmost paths are covered, and then it will once again, if the that is not the solution, it will once again back come back and check the other path which is possible for that. So here we have some theory which is related to this depth first search. So it always expands the deepest node in the current fringe. So fringe means, as we have seen the last example, a binary node. So this is something called as a node A. Then whatever the paths which are directing to B or C. So this we call it as the fringe. Okay. So fringe of the current fringe of the tree. That means it will just always go deep into the fringes for searching the tree. So if dead end occurs, as I told earlier, if B is not the solution, then it will go to C. So for that, first it will check what are the other paths of B, leftmost path of B it will check, and then in that path also, if there is one more leftmost, it will check. If that is not the solution, it will come back and then come just check the other paths. Okay. So that is, if dead end occurs, backtracking is done to the next immediate previous node for the node for nodes to be expanded, as we discussed earlier here. So whenever there is no solution from A, B, D and H, it will check for I. So if I is also not the solution, it will go back to D, and as H and I are covered and they are not the solutions, it will once again go back to B, and then check for the other path of the B, that is D, as D is already covered and even the paths of the D also covered. It has the B other path is nothing but E, so it will check the E path. Like that the backtracking is done and search for the other node, and if even other node is there, once again it will go back to the previous level. So that's how the search continues in the depth first search. So what is the advantage in this one? The advantage is that if more than one solution exists, our number of level is high, then DFS is nothing but best, because exploration is done only in a small portion of the whole space. This means that when we have a deeper tree or a deeper graph, so and the solution is present in that the last node of the deepest graph or the tree. So whenever it searches to that path, then it will get the solution. So that means if the path is very large, and DFS can do better. So that is the advantage. And even the other advantage is that if more than one solution exists also, so DFS can do better. Why? Because as it checks the solution, it can come back once again and check the other paths also to find the solution. So that is the advantage with the DFS. Coming to the disadvantage, so not guaranteed to find a solution. So sometimes what happens is there will be some loops and it will try to continue in that loop going very deep, and it may not sometime return back. So solution is not guaranteed in the DFS. So next we'll see one more example. Here we have S is nothing but the initial state and G is nothing but the final state. So there are different directed arrows, so which indicates the path to the G. So we need to track this path using DFS. So here, as we know, the strategy is to expand the deepest node first. So how is that possible? As I told earlier, it will try to explore the leftmost path, and then if no solution is there, once again it will come back to the previous level and if any other element is there, it will track and check. Once again, go back to the previous level. So just see this example. So in this, we have S is the initial state. So it has three paths, that is to the D, that is to the E, and that is to the P. So as you can see, it has D, it has E, and it has P. So first, as we know, it will always try to go to the leftmost path. So leftmost path is nothing but the whatever the D we have chosen here. So as it comes to the D, so what we have in the D, we have B, we have a path to uh, B, and path to C, as well as path to E. You can find the same thing, path to B, path to C, path to E. But C and E paths are not explored. Why? Because after S to D, it will just check the leftmost only. So the leftmost is nothing but from D to B. From D to B. And in B, what we have is only one path, that is A once again. A here, A we have not yet explored, so A here we got. But is there any arrow for that? Arrow from A is not there. Why? Because this B to A is pointed and C to A is pointed, but there is no path from A. So it becomes a deadlock, or we can say uh, dead end. It becomes a dead end. Why? Because it has not reached to the goal state. So what it will do, it will just go back to the next level, B. So is there any path available? So there is no other path available for the B. Why? Because only path for B is nothing but A, and A is not the solution. So it will go back to B. And as there is no other path, it will once again go back to D, the previous level. So in the previous level, the other path is nothing but C. So it will come to C, and after coming C, so what are the paths available? So if from C also we have only one path to A. Why? Because this D to C and F to C, but C is going to only to A. So it will come to C, and from C to A. And here also A is not the solution. So once again it will go to the previous level, that is C. And next C has no other path. So once again it will go to the previous level, that is D. And the other path of the D is nothing but we have covered B, we have covered C, and now we have to just check the path E. So in this E, the paths are to H is there, R is there. So the path from E to H, first it will be going to H. Why? Because H is the leftmost. So if from H we have two arrows to, that is P and Q. So in that P and Q, first it will just check the P path only. Why? Because it need to go leftmost. From P we have only direction to Q. So even this is also not the solution. Q is also not the solution. So it will go back to P, but there is no other path to P. So it will go back to H, and from H, what is the other path left over? P we have already covered. The other path is nothing but Q. Next, Q is also not the solution. So once again go back, that is to the H. And already we have covered two paths of H, that is P and Q. So there is no other path. So it will once again go to the previous level, that is E. From E we have covered the H path, total H path. The other path is nothing but R. So R, as we can see here, from R we have only one arrow to F. So we'll come to the F. Next, from F there are arrows to C as well as the goal state. So first it need to explore the leftmost, so that it will just go to C, and then from C there is a path to A, but A is not the solution. So what it will do, it will once again go back to C. So there is no other path. So once again go back to F. So F, there is a path, the other path, that is nothing but G. So which is nothing but the goal state. So it has achieved the goal. So that's how it will find out the solution in the depth first search. So even there are other paths also mentioned. Why? Because as we discussed earlier, there can be multiple solutions also. So this is nothing but one solution, or reaching to the goal state. So there can be even other paths by which it can reach the goal state. So you can also find in this graph or tree, that is the goal state here. So the other way is also possible to reach to the goal state. Okay, but the strategy is nothing but always expand to the deepest node. And next, how we are implementing, as we discussed, fringe is a LIFO. So fringe means, as we discussed, so we are taking A. So from this A, whatever the arrows we have, that we call it as the fringe. That means from where A is pointing to B and C. So that is what from A, the transformation to B and C is there. So fringe is a LIFO stack. So why it is a LIFO means, so as just see, whenever first we have A, it will first go to B only, as it is the leftmost, it will go to B. So it has stored A as well as B. So whatever we have in the last, so here the whatever the stack which we are following is a last in first out. So from A, it has come to B. So last element is nothing but in this stack, B is the last element. So it will be first out. That means this first, it will be eliminated. Eliminated means it will go back to A. So now we are at A. So we'll try to see the other path C. So like that the implementation is done. So the stack which is followed here is nothing but a last in first out stack. Next we will see one more example. Here the example is nothing but a state space or tree search. So successive, give the sequence of visited nodes when DFS, assuming node A is the goal state. Here, so initially we have the state A, that is the initial state we can consider, and final state is nothing but O, that is node O, which is the goal state. So there are different paths. So we need to check each path using the DFS technique, and we need to find out the solution, that is nothing but the goal state. So here, as you can find, so as we discussed in the earlier examples, it will always check the leftmost. So from A we have path to B, C, D, B, C, D as well as E. But as the leftmost is B, it will check for the other paths of the B, that is leftmost path, that is nothing but B to F. As F is not the solution, it will come once again to B. So as there is another path to B, that is G, it will go to G. Next from G, the leftmost is nothing but K. K is also not the solution, so it will come back to G once again. And G, whatever the other path left over is nothing but to L. And from L, it will move to the last one, that is nothing but O, which is the goal state. So that is how we will be exploring the path. We will see how it is exploring as just whatever we have discussed. So that A is what the first we are exploring. Next we are going to B. Next we'll see the F. Next we'll, as F up to F, it has come to the one path. So this is nothing but one path. From here, as there is no solution there, it need to return back. So that we'll be writing in another row here. Okay, just next row is nothing but G. Why? Because G, it is not in the same path as A, B, F, as it need to go back to go to G. So we are taking G in a separate row. So G, and the leftmost is nothing but K. So after this, as it has also covered the other path, that is this one. Next, when it need to explore the next one, it need to go back to G and explore the other one, that is nothing but L. And it explores this path, that is A, B. As just see, we have already covered K in the last step. So after coming to K, as it is forming the new path, the path does not contain the solution. It will be going back. So we are writing in the another row L. So after reaching L, so it will be moving to the, after it will be reaching to the goal state, that is O. The goal state of O. So this is how we explore the paths using the depth first search technique. And we'll see now the properties of the DFS, that is depth first search. So there are 4 questions for this one, the properties which we'll be discussing in the form of questions here. And here is one diagram which indicates different levels and how many nodes are there in the each level. Okay, so here as we discussed earlier example, so there we have seen something like A. From this we have B, C, D, E. Next we have some path here. So this is level 1, this is level 2, this is level 3, like that. We have different levels. We can call them as tiers. So M tiers we can write here. And next, initially whenever we are taking the first one, that is nothing but one node, which is the first node A. We can, in this example, we can take A as the one node. And next level, there can be B nodes. So B nodes indicates that it can be 2, it can be 3. So like that, it can take any number. That is, B can take any number. That is the branch. We can call it as branch. Why? Because from A we have branch to the different elements. Here in this example, B, C, D, E are the elements. So here B can be 4. Why? Because there are 4 branches from the initial element A. Like that, we can have different, there is B square nodes. Why? Because at each level, the number of branching factors will be doubling. So sometimes that branch may not be there, but uh, in general, if we take for element, the branches will be squared the next levels. So that is B square, it may be B cube in the next level. So like that. So here in this we have just pink dots which indicate the solution. So we need to explore so the first path and just next path. You can see here the lines next to this path, and in this path we will get the first solution. Next, when we try to explore this path, we will find the solution here. So there can be total last branch, last tier. We can have B power M nodes. So as I told, the properties we'll be discussing in the form of questions. So what nodes DFS expand? So as we discussed in the earlier slides also, left prefix of the tree. Always it will try to explore the leftmost node from in that branch. That is, it will go deep with the left. And could process the whole tree. As we discussed in the previous examples, it can go until the last path to find a solution. It will go onto the last path, that is, it can just explore all the tree to find the solution. So that is could process the whole tree. And if m is finite, so m is indicating the number of tires, or we can say number of levels. So takes time, that is nothing but how much is the complexity of the time with respect to this search. So in this search, the time complexity is nothing but O of b power m, where b is nothing but the number of branches, and m indicates the number of tires or number of levels. So that is the time complexity uh, in this DFS technique. Next, how much space does the fringe take? As we discussed, fringe means here if we have A, so whatever the arrows we get from A to B, C, D, E, these are nothing but the fringes. From the element, whatever the arrows which are coming, that we can call it as a fringes. So here only have siblings on the path to the root. So if we consider only siblings means the path, that is the next level. If we have the elements, the complexity will be the same as the time complexity. Whatever the time complexity we have, that is O of b power m, the similar complexity will be there. Why? Because so whenever you need to explore anything, so just see, as we have just, let us take, we have level 1, level 2, level 3. So the solution we need to explore till L3. So in level 3 there can be 1, 2, 3, sorry, and in level 2 there can be 2 branches. From level 1 we are just going to level 2, we have 2 branches. And in level 3 also we have just one. So this can have one branch, and it can have 2 branches or 3 branches. So based on that number of levels and branches, we need to calculate the space complexity also. So why we are taking the same thing means, why? Because how much time it is trying to explore the each and every element in that tree, the similar space is also being consumed. Why? Because whenever it goes in this level, as we took previous example, A to B and B to the next one, the time is nothing but A to B is one time, and B to C, B to some other element is other time. And even space, we need to store A, we need to store B, and we need to store this element also. Next, it need to go back to go to the next path. So even going back also will be consuming time, and even the space here also it will be relieved, but it need to store other elements. So the space complexity and the time complexity look similar in the depth first search. Is it complete? The other question is it complete, or we can get the solution or not? So m could be infinite. So m is nothing but the number of tires or number of levels can be infinite. So we can get the solution, but there should not be any cycles. There should not be cycles. Cycle means something like if there is a path to A to B and B to C and C to A. So whenever it is moving from A to B, so it will go to from B to C and C to A. Then A to B, B to C, C to A. So it will be just rotating like a cycle, and we can't get the solution anytime. So that is nothing but cycles. So if we avoid the cycles in the graph or tree, then we can get the solution. Our solution will be complete. but the levels that could be infinite also, as it is exploring until the deep, so it can get the solution. But the main thing is nothing but avoid the cycles. So the next question is it optimal? So it is not a optimal one. Why? Because it is always trying to find the leftmost solution. So how much is the depth? It is not knowing. So it need to go whatever the leftmost path is there. It will try to explore until the deep, and if it is not finding solution, it will once again return back and check the next path. So it is not an optimal one. So that is what the properties of the the DFS. The first is nothing but the time complexity, which is O of b power m, where b is nothing but number of branches and m is the number of tiers or levels. Even second one is nothing but space complexity, which is also same, that is O of b power m. So, and the third one is nothing but completeness. So completeness is possible, but cycle should be avoided for having completeness. Next, optimal. Optimal, it cannot be an optimal solution. So that is what the properties of the DFS. And continue supporting the channel. Also like and share the video for more people, so that they can take advantage of this videos. And in the coming videos we'll be discussing about the other search techniques in the uninformed, and later move on to the informed search techniques. Thank you all.